In this lecture, we'll analyze the computational complexity of the Fibonacci heap using the potential method. Starting point is to define a potential function. I'll define my potential phi to be equal to the number of roots present in the Fibonacci heap plus twice times the number of loser nodes. This potential function will look a little bit like magic. At the end of the analysis, hopefully it will become clear why it is that this was exactly the right potential function to use. There's one other term which I'm going to use. I'll define dmax to be the maximum degree of any of the nodes in the heap. And what we're going to prove at the end of this section is that dmax must be O of log n, where n is the number of items present in the Fibonacci heap. So let's just go ahead and analyze the amortized cost of each of the operations on the heap. We'll look at them in turn. Start off with the easy one, push. Let's just remind ourselves what push does. When we push a new node onto the heap, we just append it to the list of roots. All we need to do is change a fixed number of pointers for this, so the true cost is O of 1. And what's the change in potential? Well, the first term in the potential function, the number of roots, that goes up by 1 because we've added a new node into the root list. The second term in the potential function doesn't change at all. We don't change the number of losers by this operation. So when we combine these two together, the amortized cost is just the true cost plus the change in potential O of 1. Let's look at the next operation, Popmin. There are two parts to Popmin, and we'll look at them in turn. In the first part, we look at the root node pointed to by min item, where remember we're keeping track of which of the trees has the smallest root. So we'll cut it out and we'll promote its children. What's the cost of this? True cost O of dmax. We have to iterate through each of the children and place it onto the root list. The number of children that it has must be less than or equal to the maximum degree. We've defined dmax to be the maximum degree of any of the nodes in the heap, so the true cost of promoting the children like this is big O of dmax. How much does the potential change by? Well, we take up to dmax items and we place them on the root, so phi might go up by as much as dmax. If there are fewer children, phi will go up by less. Also, there might be some children which had been marked as losers. Remember the rule for the Fibonacci heap: when we take a loser node and place it onto the root list, we erase its mark. So possibly phi will go down by a little bit because we've erased some of the loser marks. So when we combine these two, add them together, what do we get? We get the amortized cost O of dmax, and as we've claimed at the top, this is O of log n. Next, we go through a cleanup process. In this cleanup process, we merge trees of equal degree. Let's just have a refresher to remind ourselves exactly how this cleanup and merging procedure goes. This is what the code might look like. Let's run through an example execution of the cleanup phase to illustrate how it works. First of all, we declare an array, root array, and this will have one slot for every possible degree. We've said that the maximum degree of any node in the graph is dmax, so I'm going to have dmax plus 1 slots here. And the cleanup procedure works like this. We go through the list of all of the root nodes and we place into the appropriate slot in root array. This node here, this tree, had degree 0, so I'm going to place it in the slot 0. Next one, this tree has degree 1, its root node has degree 1, so I'm going to place it in the slot 1. Next one I come to, this node has degree 0. I want to put it in the slot labelled 0, but there's already something there, and our rule says we want to merge trees of equal degree, so I'm going to merge these. I'll make the 7 a child of the 3 because we want to preserve the heap property. Okay, can I put this into my root array? No, I can't yet, because this new tree I've created has degree 1. There's already something in my root array of degree 1. I want to merge trees of equal degree, so I'll merge them. Okay, so now I have a tree of degree 2, and I can place it into root array in slot 2. Next item, a tree of degree 0, I'll put it in a slot labeled 0. Next item, there's already an item of degree 0, so I need to merge these two. I'll merge them. Remember, I'll merge them so as to preserve the heap property. I'll put the smaller element on top. This new piece has degree 1, so I can put it into the root array in slot 1. Okay, so I think it's fairly clear that as we go through this procedure, we will merge trees of equal degree and we'll end up with at most one tree of any degree. Last stage, just take all the trees we've created and put them into a list. And this will be our new root list. So let's analyze its complexity. Let's write out some symbols first. Let's suppose that it starts with T trees. T trees in the roots list, all waiting to be cleaned up and merged. Let's suppose that in the course of the cleanup it does M mergers. And let's suppose that at the end of all this procedure it ends up with D trees. Now here's an equation. T equals M plus D. If we think about what happens, let's suppose I started out with 5 trees. If I did one merge, I would end up with 4 trees. If I did 2 mergers, I'd end up with 3 trees. To think through why this equation is true, I don't need to worry about which trees are being merged. I'm just counting how many trees do I have. Each merge I do decreases the number of trees by 1. Okay, so this tells me that T equals M plus D. Now let's think of what the costs are. The true cost is, well, what does the merging procedure have to do? It has to iterate through every single one of the trees, and it has to do a certain number of mergers, and at the end it has to copy all those final trees that it ends up back into the root list. Well, let's simplify this. We've got T plus M plus D. T itself is M plus D, so this is 2 times M plus D. In the big O notation, we don't actually care about the constant, so this is just O of M plus D. What's the change in potential? We've done M mergers. Each of the mergers has decreased the number of roots by 1. So in other words, the potential must have gone down by M. If we put these two facts together, we get that the amortized cost is O of D. The M amount of work we're doing and the minus M change in potential cancel each other out. If you want to remind yourself exactly what the maths is behind this, exactly how the big O and the minus M cancel each other out, go back and review the lecture on amortized analysis. Okay, so we've said that the amortized cost is big O of D, where D is the number of trees that we ended up with. How big could D be? The largest of those trees can't have degree larger than D max, because D max is the maximum degree, so therefore D must be less than or equal to D max plus 1. D max is big O of log n, so what we have left here is O of log n. Okay, so what we've discovered is that Popmin has 2 parts, and each of the parts has amortized cost big O of log n, so the total amortized cost of Popmin must be big O of log n. Let's look at the final operation, decrease key. There are 2 possible ways that decrease key might play out. Possibility number 1, no movement is needed. We can decrease the key without violating the heap condition. This case is very easy. Let's write it out. If no movement is needed, all we need to do is decrease the key. So the true cost is O of 1, and the change in potential is equal to 0. We haven't changed anything about the number of roots or the number of losers, and putting these two together, the amortized cost is O of 1. Second case, if movement is needed, in other words, if the heap condition is violated and we need to move some nodes to the root list, well, let's just remind ourselves what the algorithm looks like for that. Here's a typical picture. Let's suppose that we have this sort of tree and we've decided to decrease key on the bottom node labelled with key 9. Let's suppose I've decreased the key to 6. This is now a heap violation, so the rule says if you have a heap violator, just cut it out and stick it in the root list. Its parent 8 has now lost a child. It had been marked as a loser previously, so now it's a double loser. So what do we do? If you have any double losers, you slice them out and put them into the root list. 5 used to have 3 children and it was marked as a loser. It's lost yet another child, so it's a double loser. So we'll repeat the rule. We'll slice out the 5 and place it into the root list. And 4, the parent, 4 has lost a child. Previously it wasn't marked as a loser, so now we do mark it as a loser, but we don't need to slice it out. So this is the end of the procedure. Let's analyze the complexity of all of this. Referring to the picture at the bottom, what do we do? First of all, we'll move A to the root list. The work involved in this is O of 1, because it's a fixed number of pointers we have to mess around with. Change in potential is equal to 1 because we've got one more root in the root list, unless perhaps A was previously marked as a loser. When we move A to the root list, in that case we'd be removing its loser mark, in which case the number of losers would have decreased by 1, which would make phi minus 1. So delta phi is equal either to 1 or minus 1. I'll just write less than or equal to 1 in either case. Then we have a certain number of loser ancestors. I'll call that number L. In this picture, L is equal to 2. We have to move L loser ancestors to the root list. The true cost of this operation is O of L because there are L of them to work with. And what's the change in potential? Change in potential plus L, because there are L new items in the root list. But each of them, previously it was marked as a loser. Now it's no longer marked as a loser. So the number of losers has decreased by L. So therefore phi goes down by 2L. So in aggregate, change in potential is minus L. And then the final piece of work that we need to do is we have to mark D as a loser. The true cost of this, there's only a single node that we're marking as loser, so true cost is O of 1, and change in potential is plus 2. Actually, to be strictly correct, possibly D is a root node. If D is a root node, we wouldn't mark it as a loser, so I'll write question mark here because we possibly mark D as a loser. True cost O of 1, delta phi less than or equal to 2 because we either mark D as a loser or we don't. So if we look through all of these steps, first part, true cost O of 1, change in potential fixed. Second part, true cost O of L, change in potential minus L. They cancel each other out. Final part, true cost O of 1, change in potential fixed. So therefore the amortized cost is equal to O of 1. This completes the amortized analysis. Let's just summarize where we got to. The cost of push amortized is O of 1. The cost of popmin amortized is O of log n. And the cost of decrease key amortized is O of 1. Now's a good time to look at this proof and to think, why is it that we had to choose exactly that potential function? There are two important parts to this analysis. I'll label them here. This is one part. In the cleanup merge procedure, we had to do M mergers and we had to iterate through T trees. In the decrease key procedure, we had to iterate through L loser ancestors. The big idea is that both of those steps, which we've just labelled, involve a variable number of iterations. What do I mean by a variable number of iterations? Well, if we think, for example, of decrease key, we don't know how many iterations there'll be, and yet we want our overall cost amortized to be O of 1, so I need to pay for all those unknown number of operations. And that's exactly what this potential does. These iterations have already been paid for by all the earlier operations which pay into phi, all the earlier operations which increase phi, which increase potential. So the potential function phi that we designed reflects a very careful balance. We designed it so that every time you do something like a push or every time you mark something as a loser, you increase potential by a little amount, because you know that in the future, either in the decrease key stage or in a Popmin stage, you will have to pay the price for all of those things you did. Every time you promote a node to the root list, you know you will eventually have to clean it up. Every time you mark a node as a loser, you know that decrease key might have to go through them and iterate through them. So we pay a price, we increase phi when we do those things which are going to incur a downstream cost, and then when we do actually incur the downstream cost, the potential decreases, and that pays for the true cost of those expensive operations. There's one more thing to prove. In the analysis of Popmin, we made heavy use of this fact, the fact that the maximum degree of all the nodes in the heap is big O of log n, where n is the number of items in the heap. So now it's time for us to prove this. Here's a slightly more general theorem called the shape theorem. If a node has d children, then the subtree rooted at that node has above or equal to fd plus 2 above or equal to phi to the d nodes. Let's just define some terminology here. F is the Fibonacci sequence. F1 is 1, F2 is 1, F3 is 2. You sum up the preceding two items. F4 equals 3, F5 equals 5, F6 equals 8. These are the Fibonacci numbers. And phi is the golden ratio, which is roughly 1.618. In this theorem, the second inequality, this thing, the fact that the d plus second Fibonacci number is above or equal to phi to the d, that's just pure maths. You can look it up on Wikipedia and try it. Pure algebra. We're not going to bother about analysing it here. What's interesting for us is the first part of the theorem, which is a statement about the operation of the Fibonacci heap. Before we go on to prove it, let's just look at an illustration. Here I've got some trees that could arise during the operation of a Fibonacci heap. Let's just see what they say. If I look at the first node first of all here, this node has degree 0. The theorem says that the total number of nodes in the tree, what's the total number of nodes in the tree rooted at this node? 1. Theorem says that it should be above or equal to f sub 2. f2 is 1, so that's correct. Let's look at the second thing. D equals 1. The number of nodes in this tree is equal to 2. Theorem says it should be above or equal to f3. f3 is equal to 2. Yes, good, the theorem worked. Here, D equals 2. The number of nodes in the tree is equal to 4. Theorem says that this should be above or equal to f4. f4 is equal to 3. Yes, good, it worked. The rest of the trees I'll just look at the root nodes. The theorem, of course, applies to any node at all in anywhere in the heap, but I'm just going to be counting how the root nodes behave for the purpose of this illustration. These three trees all have degree 3. Number of nodes in this one is 8. Number of nodes is 6. Number of nodes is 6 again. It's only the tree with the smallest number of nodes where the theorem bites the hardest, so I won't bother inspecting the first tree with number of nodes 8. I'm going to look at the second tree where the number of nodes is equal to 6. The theorem says that this should be above or equal to f sub 5. f5 is 5, number of nodes equals 6. Yes, good, the theorem works. Okay, so that's the theorem. What does the theorem have to do with the amortized analysis that we did a moment ago? Let me write out the big result here. Corollary. In a Fibonacci heap with n items, the maximum degree is O of log n. The proof of this corollary is pretty straightforward, and it's left as an exercise on the example sheet. I won't prove it in this video, but I will make a note of a very closely related result. When we looked at the binomial heap, we made the following observation. Firstly, we said a binomial tree of degree k has exactly 2 to the k nodes in that tree, and with a very little bit of manipulation, one can show that this implies that a binomial heap of n items has max degree O of log n. Also, it has number of trees O of log n. These were fairly straightforward results to check for the binomial heap, and the proof of the corollary is along very similar lines. The proof of the shape theorem is really a curiosity. It's not something which has very general applicability, but it's also not all that hard to prove, so we might as well just go through the proof now. The proof comes in 2 parts. First part is argued like so. Let's consider an arbitrary node x in a Fibonacci heap at some arbitrary point in the execution. What I want to imagine is that we've inserted a breakpoint into our code. We're going to stop the execution and we're going to inspect the state of the data structure. Let's imagine that at that point in time where we've stopped, we find that the node x happens to have d children. Let's label those d children. I'll label them y1 up to yd in order of when those children became children of x. So if we think back to what must be the events that preceded this breakpoint, at some point in time we had the node x. At some point in time, y1 became a child of x. At some point in time, y2 became a child of x. So y2 became a child when x already had y1 as a child. How could y2 have become a child of x? The only place in the algorithm where a node can become a child of another node is during the cleanup, the Popmin merging procedure. Remember, the rule for merging is if you have 2 roots of equal degree, then merge them. X already had a child. Y2 must have had a child also. So let's write that out. When x acquired y2, x had a child, so y2 had a child. That's the only way that y2 could have been merged in. Let's look at the next one. At some point in time, y3 became a child of x. Similar reasoning says that when x acquired y3, y3 had 2 children, and so on. It's also possible that some of the nodes could lose children. Let's suppose that at some point in time between acquiring y2 and the point in time that we're looking at, that y2 lost a child and y2 became marked as a loser. This could have happened to any of the nodes, in fact. So let's summarize what we've learned. We've discovered that at the breakpoint where we've decided to look at things, y2 has above or equal to 0 children. That's a pretty trivial thing to say. It must have had one child when it was acquired. It might have lost one child since then, so it has above or equal to 0 children. Y3 has above or equal to 1 child. It had 2 children when it was acquired by X. It might have lost one in the meantime, so at the breakpoint it must have above or equal to 1 child left. Y4 has above or equal to 2 children, etc., all the way down to YD has above or equal to D minus 2 children. We ought to be a little bit more careful in this proof. What we haven't taken account of is that something might have happened in the meantime. We labelled Y1 up to YD to be the children that X has at the breakpoint, but it may have acquired other children and lost them in the meantime. Let's imagine that X acquired another child after Y1 and then it lost it at some point later in the future. So if at some point in time X has some further mystery child, let's call it Z, X might have a child Z, in which case we know that Y2 has above or equal to 1 child. It's got at least 1 child because X has at least 1 child. It could be more. Likewise, Y3 has above or equal to 2 children at that point in time, and so on. The equalities I've written down at the bottom of the page, they still work. They're still the right way around. I ought to be more precise about one other matter, in order of when they last became children of X. What am I talking about here? Well, it is conceivable that X acquired child YD very early on, then it lost child YD, and then it acquired child YD again later on. For the purpose of these bounds, I'm only interested in the nodes Y1 up to YD at the last point in time at which they became children of X. That's the order in which I want to place them. Okay, so that's some very technical and careful thinking through corner cases, but all of this theorem still works. The statements at the bottom, they're what really matter. Let's fill it in. We might as well stick in Y1 has above or equal to 0 children. That's a contentless statement. But this bunch of inequalities, this is what really matters. I'm going to call this the grandchild rule. Grandchild rule is that a node with children, let's call its children I equals 1 up to D, has above or equal to I minus 2 grandchildren via node I. And what we've just proven is that any node in the Fibonacci heap at any point in time satisfies the grandchild rule. Next part of the shape theorem. Let's consider a totally arbitrary tree, all of whose nodes obey the grandchild rule. Remember, the grandchild rule says a node with children I equals 1 up to D has at least I minus 2 grandchildren via child I. This second half of the proof, this is a pure math thing. I'm not talking about the Fibonacci heap anymore, I'm just talking about the space of all possible trees which satisfy certain inequalities. And let me define ND to be the smallest possible number of nodes in a tree which satisfies the grandchild rule and whose root has degree t. So let's see what we can say about ND. ND equals, let's sketch the tree first. A tree with a root and then a certain number of children. I'm going to write out an equation, 1 plus n naught plus n naught plus dot 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 plus n d minus 3 plus n d minus 2. Where do all these terms come from? Well, Let's just count how many nodes there must be in this tree in total. The very first term, the 1, refers to the root node itself. Now for the others, let's work backwards. And let's ask, how many nodes must there be in the tree rooted at child D? This node has above or equal to D minus 2 children. That's what the grandchild rule says. The smallest number of children there could possibly be in this subtree is nd minus 2. And likewise, all the other terms come from the other children. nd minus 3 comes from child d minus 1, and so on, all the way down back to child 1. Now to simplify, these first terms, the 1 plus n0 plus dot 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 plus nd minus 3, I'm going to call these all just nd minus 1. If we think about what the equation says that nd minus 1 is equal to 1 plus n0 plus dot 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 plus all the way up to nd minus 3. That's just what the entire equation says. In other words, nd is equal to nd minus 1 plus nd minus 2. So what we've recovered is exactly the Fibonacci recursion. Each n is the sum of the two preceding n's. It's a recursion. We better just state what the initial boundary condition is. n0 is the smallest possible number of nodes in a tree whose root has degree 0, so that's obviously 1. n1, smallest number of nodes in a tree whose root has degree 1 and satisfies the grandchild rule. This comes out to be 2. It's just the tree whose root has one child. And then for the rest of it, we can just apply the recursion. n2 is 3, n3 equals 5. And if we compare this to the Fibonacci numbers f1 is equal to 1, f2 is equal to 1, f3 is equal to 2, f4 is equal to 3, and so on. So in other words, when we put these two together, we see that nd is equal to fd plus 2. So let's just recap. What have we proved here? We've proved, first of all, that at any point in time, a Fibonacci heap satisfies the grandchild rule. And then we proved a pure mathematical result. We proved that if we have a collection of nodes, all of which satisfy the grandchild rule, then we have a bound on the total number of nodes. So, putting these two facts together, this proves the shape theorem. And just to remind ourselves what all this was for, if we have proved the shape theorem, then that gave us a corollary which said what the maximum degree of any node in a Fibonacci heap was. We decided maximum degree is big O of log n. And we used this fact when we were analysing Popmin to conclude that Popmin has amortized complexity O of log n. The Fibonacci heap algorithm is a really beautiful and clever balancing of different effects. The Fibonacci heap data structure is a beautiful and elegant balancing of different. The Fibonacci heap data structure is really an extremely elegant and intricate balancing of different forces. To make sure that you truly understand what's going on, and why the potential had to come out as it was, and why all the rules work together exactly as they do, the only way to really persuade yourself that you understand it is to ask, if I wanted to design it from scratch, would I be forced to come up with exactly the same solution, or is it possible that there are different solutions which would work just as well? So here are some example questions that you might investigate. Let's say if we allowed nodes to lose up to 2 children before dumping them in the root list, would the amortized cost change? If we only wiped clean the loser mark during the decrease key operation, would the amortized cost change? What I mean here is, we said during Popmin, when you promote children to the root list, you will erase the loser mark if any of the children had been marked as a loser. If we just got rid of that part of the algorithm, would anything significant change, or is that just an optional feature? So this is the sort of question you should ask yourself. You should ask yourself, could I reinvent the Fibonacci heap myself from scratch? And what are the bits of the algorithm which are fixed, and what are the bits of the algorithm where I have wiggle room?